In this video, we'll work through the solutions for design problems 1 and number 8 from chapter 23. Okay, so for number 1, we want to use a FSM to design a synchronous 2-bit binary counter that has an up and down input. And we're also going to, when up and down are both simultaneously asserted, the counter will clear. And if neither up or down is asserted, then the counter output stays the same. So for this problem, I'm just going to go straight to the next state table because it's a fairly simple circuit. It's a 2-bit counter, and there are 2 inputs, up and down. If up and down are both 1, it doesn't matter what my current state is, I'm going to force the next state on my counter to be 0. And if both of my inputs are 0, then I'm simply going to stay in the same state. With 1, 0, I count up, and 0, 1, I count down. So for the circuit, I could build something that looks like this, where I have a 2-bit state register holding my 2 bits, my 2 state variables, Q1 and Q0, and then a next state decoder, which is essentially implementing this table, our next state table. Or in Verilog, you can map this using a behavioral description. I could also map this directly down to gates and create the combinational circuit that generates the inputs into my flip-flops or state register. So this is what it would look like if I implemented directly with 2 T flip-flops and some combinational logic. Okay, let's look at problem 8. We want to use an FSM to design a binary counter that counts in the following sequence. It has an active low asynchronous reset input that forces the count to be 2 when asserted, otherwise allows the circuit to count, and the circuit is also self-correcting and directs unused states to the state associated with the count value 17. Okay, so there are also different ways that we could solve this problem. Okay, so one way to design this is by using, I have 5 states, 5 numbers I need to count, so I'm going to need at least 3 flip-flops. Okay, so I have 3 flip-flops that hold the state of my circuit because I have 5 different numbers I'm counting. And I went ahead and written down the states 0 to 4 here that correspond to my 5 numbers. And I have up to 30, so I'm going to need 5 bits for my output here. I've called it Z4 to Z0. The last 3 combinations for my state variables I'm not using. So the output, I'm just marking those as don't cares. For the next state, however, so the first 5 would count as I'd expect, they just move on to the next sequence. But for the unused combinations, because I want this circuit to be self-starting, I want it to go to state 17. That's why I'm making the next state be for these last 3 be 1, because this is the state associated with the count 17. Okay, so this would be my high-level description of the circuit. I have a next state decoder, which is basically described by these 2 parts of the table. And then I have an output decoder, which is basically described by this section. Another way that I could design this circuit would be to use a state register that has 5 bits. And so this would be another solution. The trade-off being that now I have a larger register, 5 bits rather than 3, but now I won't need an output decoder because my output is just the state, the 5 bits of my state register. And then finally, another solution would be to take this down to the gate level. So I'd have 3 T flip-flops with their flip-flop inputs generated by the following Boolean expressions based on the current state, Q2, Q1, Q0 of those flip-flops. And my outputs, I could also derive Boolean expressions.